Okay, so the gas laws, as I said before, I think you'll enjoy because they're pretty simple. They're pretty straightforward. It's things I think you can figure out and understand. Let me get this the other way. Because you deal with these on an everyday basis. Hot air balloons will fly because of the gas laws. Because we know that when gas expands, it becomes less dense, therefore it tends to rise. So gas laws, as we go through these, you'll be very happy with them. Okay, so gases are one of the four phases of matter that we know of. There's a solid, there's a liquid, there's a gas, and there's plasma. Now, the Bose-Einstein condensate is also a state of matter, but it has very little relevance to us, so we still might talk about it. Plasma, a little bit more with lightning and stuff, but not something we use on an everyday basis. Okay? We know it has no definite volume, no definite shape. It just kind of roams where it wants to. Gases tend to be all around us, actually in us. You know, we're gaseous creatures as well, some of us more than others. But gases are typically have a low density. They are typically compressible. They're the only state of matter that we can compress, and they're fluid-like. Water, we know, or liquids or fluids. They pour. Gases pour also. Gases can move like a river, like a stream. They're very fluid-like. So gases can also be fluid-like. We okay? Yes?
So this is one of the four major states of matter? I thought there was only... Oh wait, no, there's...
Okay. Now there's something called the kinetic theory. The kinetic theory says that all matter is in motion, basically. Okay? All matter consists of tiny particles. And what are those tiny particles we think make it matter? Atoms. Good. So all matter is made up of atoms, which are tiny particles, and all those tiny particles are always in constant motion. Always. They don't stop. Even at negative 210 degrees Celsius, they don't stop. They still have some motion to them. Only when we hit absolute zero, and we'll talk about that in a minute, will they actually come to a complete stop. So all particles are moving. The particles in a gas have random motion. They have constant speed. They have perfectly elastic collisions. They bounce off each other with the same energy that they collide with each other. They are very mobile, very active particles. And they have an insignificant volume. You know, I can just breeze through the air and nothing's bothering me. If I hit the table, I'm like, oh, for gosh sakes, I hit my leg. You know, tables have a significant volume. Air doesn't. I mean, I can turn around and do all kinds of things with air. Air doesn't have that kind of volume. And the motion of air particles are random, they're constant, and very much elastic-like. Random. Rapid random. Okay? You know, they didn't even think air was anything at one time. They didn't know what it was. They didn't think it was there at all. Air just was whatever it was. But it didn't think it had mass, wasn't made up of anything. They just thought it was just invisible something. Until there's a story about this guy, a scientist was working at his desk, and a chicken jumped off the table, off the windowsill, and hit the floor, but when his wings flapped, it blew his papers off his desk. He's like, how'd those papers move? For papers to move, matter has to move something. Matter can only move matter. Energy can't move matter. Matter has to move matter. So whatever the chicken did made the papers move. And he realized it was the air. Air must have particles. Now, I have this fun thing I've gotten out before. Yeah, right in the face there. You can feel it go by you even after. It took a second, didn't it?
I want to feel it.
What I had said. Here you go, right in the face. Okay? So, air. Oh, Ethan's hair, whoop, flipped up. Okay? It has mass. If it didn't have mass, it could not be moving. Darn. Sarah, I will get you. Your hair, golly. Did you stop? There you go. Okay? It hurts after a while, though. Okay, so this is called an air cannon. Just hairy. You know, like you hit these. I always sit back and try to like little things on the ceiling. But it takes a second for it to reach it there. Okay? So air has mass. Air takes up space. Air is matter. Okay, that was some conclusion to come to. They didn't think that at all. All collisions between gas particles are completely elastic, supposedly. But they bounce off with the same energy they hit each other. It's really not true, but we like to think that. Okay?
Why is it not true?
Because whenever you have any type of collision, you're always going to transfer some form of energy to some other. There's a Le Chatelier's, oh, not Chatelier's, what's his, oh gosh, it's Le Chatelier's. But there's an equation we use. There are some variations to how they hit each other and how much energy they're not 100% elastic. I can't remember what that's called though.
CF theory.
That's CF theory. No. My theory is that we have 14 days left and we can do this. Okay? So gas pressure is caused by all these little particles. Mr. Reeve is shooting me with a laser. He doesn't know I'm taping. So Mr. Jonathan Reeve. No. Anyway, I know, and a funny call. Stop shooting me. But anyway, so gas pressures result from all of these particles striking the walls. You know, when you get bloated from your gas in your belly, if you eat White Castles or Skyline with the onions, the reason is the gas builds up in your intestinal area, and it's moving. It's bouncing around, and it's hitting your intestines and making you go, whoa, I feel so big. Okay? That's how balloons blow up. The particles strike the outside of the balloon, and the balloons then appear to be filled up. They may not be completely filled, but they feel filled because it's pushing on the outside of the balloon. Kind of like that little container. Pressure is the amount of force applied to an area. So P equals force divided by area. It's the force divided by the area. And we'll talk more about this when we start talking about more pressures. But in order to determine force or pressure, it's the force over a certain amount of area. Like right now, there's a force on this piece of paper.
Gravity.
Over this area. No. Well, that is true. Gravity is working on it. Okay? Now, have you ever looked at a spray paint can and wonder how it works? One thing is, there's nothing really, not mechanical, but you know, what makes that stuff spray out? What is in there allowing that when you push the little nozzle down, it goes psh, and sprays out? Because they put some type of propellant in there, a gas that most of the paint that's in there is halfway, 3/4 way filled up. The rest of it's just gas. So when it's highly, highly, highly pressurized, so when you give the paint somewhere to go under all this pressure, it's going to force its way up the nozzle and come out of the can. But once this pressure drops, like down here somewhere, it's hard to get out the paint. It seems like it's done. It comes out, but not nearly with the force it used to, right? So that's why, you know, some people do stupid things like put paint cans in fires, which is terrible because one, they're pressurized to begin with, but two, the shrapnel could come out and really, really hurt you. Excuse me? No, I don't. No. Okay? Pressure conversions. Now, we use a couple more often than not, but there are many different types of measurements for pressure. These are some of them up here. Atmospheres is ATM. Torricelli, millimeters of mercury. We use inches of mercury in the weather here in the United States. Kilopascals per square inch. If you've ever put up a tire, they ask you what the PSIs are. Okay? These all are types of pressure. Just like, I call things a street. Some people might call it, a street or a way. If you go to France, it's called a rue. If you go to Germany, it's called a Strasse. I think it's ST. I think it's a Strasse. There's different terms. I may be completely wrong on that last one. But there's different terms for the word street. There are different terms for pressure. They all have different quantifiable amounts, but they all equal. 6 one way, half dozen another. Okay? Same type of thing. Equivalents for pressure are this. 1 atmosphere will equal 760 torr. It will also equal 760 millimeters of mercury. And it also equals 101.3 kilopascals. And it also equals 14.7 psi. It also equals like 11 point something, or no, 29.9 inches of mercury. These are all the exact same thing, but with different units. These are all equivalent to each other. You might say 1 atmosphere, I might say 760 torr. He might say 101.3 kilopascals. Lexi might say 14.7 psi. But we're all speaking the same language. We're just using different terms. Does that make sense? Yes? So when we convert them, question. How many atmospheres are there in 892 torr?
1 in 40.
Yep. So, but what I expect you to do is this. I expect you to write down your given. Your given is 892 torr. Now, if you look on the back of your periodic table, there's a column that says gas laws. So get your periodic tables out, please. You see at the very bottom where you see all those different units of the column of gas laws. Do you see it? The column that says gas laws and go all the way down the bottom. Yep. What is equivalent? So if I'm trying to get rid of torr and get to atmospheres, whatever I'm trying to get to goes on top. Whatever my given is goes on the bottom. What's my equivalency between atmospheres and torrs? Okay, so 1 over 760. 1 atmosphere equals 760 torr. Correct? So my torrs cancel out. 892 atmospheres divided by 760 gives me what? 1.17 atmospheres. That's how you do it. Does that make sense? So your conversions are very easy. It's just a, one-step conversion. But use that part at the bottom of the table, okay? Now, you also have to look at temperature. That's something else we're going to be converting. When we do gas laws, you must use the Kelvin scale. Do you know what's wrong with the Celsius and Fahrenheit scale? The definition of temperature is the average kinetic energy of particles. The average kinetic energy. What's wrong with Celsius and Fahrenheit? They have negative numbers. And you can't have negative energy. You can't. It doesn't work that way. If you're measuring how fast particles are moving, there is no such thing as negative energy. Well, there is in the, personality-wise, but not in the physics world, okay? So you can't have negativity there. So it doesn't make sense when we look at Celsius, or it's also called centigrade, that you have a negative 273. When we measure, it's like negative 10 degrees Celsius, or negative, something Fahrenheit. It can't happen. There is no such thing as hot or cold. Those are just qualifying things for where the particles are moving fast or particles are moving slow. Sam, I expect you to sit up, please. Okay? Particles are moving really fast, we say it's hot. If the particles are moving really slow, we say it's cold. But hot and cold really have nothing, I shouldn't say nothing have to do with temperature, but they don't tell us what temperature is. Temperature is how fast particles are moving. Because when those particles move fast, they strike against the thermometer and make the thermometer rise. When they're moving slow, they don't strike as hard or as many times, and the thermometer comes down. Does that make sense? So we're going to use Kelvin, because Kelvin has no negative numbers on its scale. This is what it should be. There's no degrees with Kelvin, it's just Kelvin. There's degrees Celsius, degrees Fahrenheit. Kelvin is just Kelvin. Freezing point of water is very important. It is 0 degrees Celsius, 273 Kelvin. Boiling point of water, 100 degrees Celsius, 373 Kelvin. You will need to know these. And an absolute zero. Absolute zero is when we believe all matter will stop moving. Matter at negative 260 degrees Celsius still has some energy. It is still moving somewhat. Only at absolute zero does it stop. We've not reached absolute zero. Not there. Yes?
Do you get colder than absolute zero?
No, not that we know. We've never reached absolute zero. But it doesn't make sense, because if absolute zero tells you that all kinetic energy is gone, and if kinetic energy is temperature, then there's no way you could get beneath zero. This is the point where all matter stops moving. Yes?
What's the opposite of absolute zero?
Infinity. I mean, you could probably get as hot as you want to. I mean, some suns are, 2,000, 12,000 degrees or whatever. So it could be whatever.
How low have we got?
I think we're within, if I remember correctly, like millikelvins of absolute zero. That's where they found the Bose-Einstein condensate way at these really, really cold temperatures. Matter stops moving the way it stops acting the way we expect it to move, and because of that, it changes its phase almost, and that's how that's a new phase. But you've got to be way down here to see that. Okay, and basically, the way you get rid of heat energy is to put it near something colder. Well, if there's nothing colder than absolute zero, how do you cool it off? You cool it off by using, they use lasers to basically force the atoms to bounce around, and as they bounce around and they lose energy that way. Yes?
When you're putting switch or something, if you put in absolute zero, is your atoms stop moving? Did you
Come out of it?
Yeah.
No. I wouldn't think so.
That would be cool.
Yeah. I think that what's it called? Cryological freezing and stuff like that. I mean, I know they can do it. Some animals do it. Frogs do it every winter. Some frogs do, because they have an antifreeze in their bloodstream, and frogs can dig down into the mud and actually freeze over the winter time. But their heart still goes very slowly because they have a little bit of antifreeze in their blood. And then when spring comes, they thaw themselves back out. So if you ever find a frog buried, sometimes you pick it up and someone's frozen solid. It's like, what the heck?
Do you
But
think
it's probably
ever
alive.
be possible for Cairo and humans?
I know people have talked about it. I think done with the right measures, why not?
I think it'd be really hard.
I think it'd be hard because we're such a multicellular thing. but, and I think your cells keep aging even though you don't, or, I mean, makes you, I don't know. I'm curious to see what happens, but I don't know. I mean, they keep like sperm cells alive and egg cells alive by freezing them, so who knows? Okay, in a lot of countries, we're about one of the only countries that still doesn't use Celsius. So if you ever go abroad, they all use Celsius. So if you're around 22 degrees Celsius, that's about room temperature. It kind of gives you a good guideline of where you are if you don't know anything else. But with cell phones, you can easily convert things. Okay, so far so good? Okay, how do you go back and forth between Celsius and Kelvin? Does anyone know? No, that's Fahrenheit. So if I want to know Kelvin and I have Celsius, what do I have to do? If you want to look back at this, notice what happens on each of these. What's the difference between Celsius and Kelvin? 273. So if I know Celsius, I need to get the Kelvin. I just add 273. Very simple. And if I want to know Celsius and I have Kelvin, what do I do? Subtract 273. Does that make sense?
Yeah.
Okay. So